Welcome back. Let's do another ANOVA. Promise this is the last one. So now we're doing two-way ANOVAs instead of one-way, and we will talk about what that means right now. So previously, one-way ANOVAs, right, the one referring to the one factor or independent variable. And now in this last type of ANOVA, we are looking at multiple factors, multiple independent variables. So today we're talking about two-way between subjects ANOVA. So what is this ANOVA? Well, as just stated, this means that we have two factors, and I'll give you a heads up. I'm going to move fast for some of this because, yeah, at this point you've heard a lot of this, and I assume that you can just go back through and look at some of this. Um, but yeah, so key thing here, we're still looking at different participants in this particular case. It's just across multiple levels of two factors rather than just one. And so in terms of how we identify factors, broadly speaking, we use letters to identify these, so factor A and factor B. And if we do a multiplication sign, like A times B, that can be used to refer to a variety of things. For one, we could be referring to the factors or the analysis themselves. If we said like a 3 by 2, um, in that case, we're referring to the levels of each factor. But if we just say like A times B, we're referring to those specific factors and the interaction between the two. Interaction is a term that I guess we haven't really used statistically in this course. So if you bear with me, we'll get to that here shortly. But yeah, so I mentioned we talk about the levels numerically. Yeah, apologies. These are wordy slides. But for example, say we had two factors. One is size and one is color. So factor A is size, small, medium, large. And factor B is color, say it's dark or bright, however you classify those. I'm not an artist, obviously. Then we would call this, for example, a 3 by 2 ANOVA, right? So we have three levels of factor A, small, medium, large, and two levels of factor B, dark and bright, right? So one example of how we do that. Some new notation, P is the levels of factor A. So in that example you just saw, P would be 3. Q is the levels of factor B. So again, the previous one, that was 3 by 2. So Q would be 2. And the combination of one level from each factor is called a cell, right? So just like cells in Excel or in like a spreadsheet program on your computer, we call those individual squares cells. That's what we call those. And so in this case, a cell is a similar concept. And I'll show you some tables here that will hopefully depict that a little more. But overall, the total number of cells is going to be equal to P times Q. So for example, in like a 3 by 2, we would have a total of 6 cells, 3 times 2. Total number of participants, so big N is equal to small n times P times Q. Um, yeah, pretty straightforward, hopefully, at this point. Three types of designs. I don't want to spend a lot of time on this, honestly. Yeah, because I think that this could get even more confusing. Or if you're worried about like the notation and separating these terms, you might be getting it too deep. Basically, there are different ways we could think about this, just based off of what specifically we're looking at across all of the cells. So in this example, two between are between subjects. In each specific cell, we have different participants. So like here we have type of rank and branch of service, Army, Navy, Marines, and enlisted in officer. And so here we'd have a 3 by 2, right? 3 by 2. And we have 5 people who are enlisted in the Army, 5 enlisted in the Navy, 5 enlisted Marines, 5 Army officers, 5 Navy officers, 5 Marines officers, right? So 30 total participants. Here it just means that there's going to be different people in each cell. Another one between, one within, or mixed. In this example, right, we have different participants at each level of one of the factors. So in this case, you can see that we're looking at this across class level. And so we have 5 freshmen, 5 sophomores, 5 juniors, and 5 seniors. And in this case, what are we doing here? We're recording the number of times students seek advice from different authority figures, right? So of the 5 freshmen, how many times do they seek advice from parents and teachers? Same for the 5 sophomores, same for the 5 juniors, same for the 5 seniors, right? So just a slightly different way of looking at this. grouped or distributed across levels of one of the IVs. And so in this example, it's the same participants and everything, right? So this is a taste perception study, and we measured the amount consumed of a solution mixed with two different concentrations of sugar and different flavors. Really weird study. Maybe you work for, I don't know, Kool-Aid. Big Kool-Aid is out to get you. That's a corporation I can get behind. Big Kool-Aid. Okay, I'm getting distracted. Um, yeah, so basically, like in this example, we'd have 5 participants in each cell, so each would get like 2%, 5%, 10% of orange, and then the same 5 would also get 2, 5, and 10% of banana. Right, so just some examples I at least wanted to mention and explain what's on the slides. Sources of variation. Key thing here is that we have main effects and interactions. Um, I'll get to those in a sec. Yeah, here's the graphic if you want to look at it more closely. But I'd prefer to spend time talking about main effects and interactions. So in ANOVAs, we're looking at group means, right? Whether they vary significantly, and in the case of a two-way ANOVA, there are several different ways group means can vary. So it could be in the rows, could be in the columns, could be in the individual cells. And so therefore we're computing 3 hypothesis tests. 2 are main effects. So in other words, that's a main effect of factor A. So in other words, it's basically an ANOVA just looking at factor A. Another is a main effect of factor B. So it's kind of like that individual ANOVA. And then one ANOVA is an interaction in which we combine both factors A and B. So in other words, yeah, it's like we're doing one look at factor A alone, one look at factor B alone, one look at the whole picture, right? To kind of really identify what's going on here across these different possible effects. Yeah, so like I said, a main effect determines whether group means significantly vary across the levels of a single factor. So yeah, same equations as always, just slightly different notation, but overall, yeah, in this case, I guess variance of group means for factor A over variance attributed to error, right? But again, here it's basic same concept we've been doing. The interaction is where that multiplication comes in, so A times B. And again, here each letter refers to a factor. Oh boy, yeah, this is kind of wordy. This is one of those things that helps with graphs, which I'll show you right on the next slide here. So basically, an interaction is telling us if levels of one factor significantly change across levels of a second factor. And so, like I said, the best way to interpret this is to graph it out. And so in the practice exercises you'll do this week, I'll ask you to do this in Jamovi. And so, yeah, this can be obvious when it's graphed. So basically, if 2 lines are parallel, then there is no significant interaction. So for example, let's do C down here. This is relatively straightforward. So here you can see that we have the 3 columns or bars, I guess, or points on the x-axis for the 3 levels of factor A. And then we have a line for factor B, level 1, and then a dotted line for factor B, level 2. Right, and so we can see here that across levels of factor A, level B1 increases, but the same is true for B2. Right, so therefore we wouldn't say there's an interaction because regardless of which condition of B you're in, your scores are still increasing as you increase your levels of factor A. Whereas an interaction means that the lines cross, or if the lines cross, then there is possibly a significant interaction. It's not a guarantee, so I want to be careful with how I express this. I guess I'm saying right here that there is a significant interaction. Most of the time, if they cross, you will see one. I guess I don't want to say it's guaranteed because maybe there's a statistical anomaly that I'm not considering here. But generally speaking, when the 2 lines touch or cross, that's a sign of an interaction, right? So you can think of it simply that way, right? Like we're looking at multiplication, that little time sign. We kind of want our graph to show something kind of like that too. And if it does, then it means that there's some significant interaction. So in here, you can see that like in figure D here. For level B1, as you increase from A1 to A3, our scores increase. Whereas for level B2, as we increase some levels A1 to A3, our scores actually decrease. right? So that's the key thing we're referring to with an interaction, is that across all the different levels, all the different cells, there's a different story to be told, right? Okay, and so with that, there's a lot here. Basically, this is listing all the possible outcomes we can have here. So nothing significant. We have significant main effects, or significant individual main effects, significant interaction, or some combination of those. Assumptions, as per usual. Let's just do an example here. So, broadly speaking, the more sugar we consume, the more we tend to like sugary foods. That's easy enough to understand. I can certainly vouch for that anecdotally in my personal experience. So let's say we have a hypothesis that a person's level of sugar exposure can interfere or distract them during a computer task when food is present. So in other words, if I'm a person who eats a lot of sugar and I'm at work and there's a bowl of candy in front of me, I'm probably going to be focused on the candy rather than on the work I'm supposed to be doing on the computer. And so let's say we do a study just assessing that, right? So we have a survey about people's sugar consumption, and then we use that to categorize them as either low, moderate, or high exposure to sugars. And then we have everyone do a computer task with, some of whom have a buffet of sugary foods in front of them, right? So it's like I'm working at a computer and there's a bowl of Snickers, bowl of Three Musketeers, bowl of, I don't know, whatever candy comes to mind for you. That's what came to mind for me. Um, and then there's some other groups or other individuals who do the exact same computer task, except there's just papers in front of them, right? There's no candy, which is, that'd be a really sad day. Feels like a waste of your time, right? Going in to do a study and you don't even get candy. Anyway, and then we assume that slower times on the computer task indicate greater distraction, right? Because they just weren't working as quickly because they're distracted, potentially by the bowl of sugar right in front of them. And so let's do an ANOVA with an alpha of 0.05. And so you can see this table here if you want to break it down. But yeah, so exposure to sugars and buffet of sugar foods. So for example, 9 people completed the computer task who were low exposure to sugar, and there was not a sugary bowl of candy in front of them. Whereas 6 people had low exposure to sugar, but there was a bowl of candy in front of them, right? And so on for the various cells. And so if we just take the means here for each of these cells, so for example, mean here is 9, mean is, oh yeah, I was giving you the wrong numbers, I'm sorry. There are 6 in each cell. Yeah, I'm sorry. I was thinking N instead of M. This M represents the mean, and if we just graph the means, it looks like there's probably going to be a significant interaction here, right? So we can see if the buffet was present, those who were high exposure to sugar took longer on the computer task than those where the buffet was absent, right? And so on and so forth. You can interpret all these individual points to clearly show that there's some kind of interaction occurring. So let's explore the nuances of that. And so let's follow our 4 basic steps. State the hypotheses. Here we're still doing equal and greater than 0. Basically, we're stating that the means do not vary or the means do vary across these different conditions. Oh wow, the animations are bad here. I apologize. Set our criteria. Go through our degrees of freedom. So just plugging stuff in. P minus 1, Q minus 1, and so on and so forth. I'm not going to bore you with all the explanation for each of these. Yeah, and an important note here is that for each hypothesis test, for the 2 main effects and for the interaction, we will need different critical values of F using all of these different degrees of freedom. So I just wanted to mention that now, and then in step 4, we'll come back to that. Okay, so compute the test statistic, just like previous ANOVAs. We have lots of like sub-steps here. So diving right in first, find N, P, and Q. N here is 6, right? I think I misspoke previously. We have the same 6. Actually, no, I don't know. I am screwing up, and I'm just going to stop. N is 6, right? Little n is 6, meaning there are 6 in each individual cell. P is 3, right? That's the levels of factor A, low, moderate, and high. And Q is 2. That's the levels of factor B, absent and present. We're going to do all this math Here the table is bigger, but it's the same concept. So for sum of x, we sum up all the individual observed scores, top and bottom. Same thing for squares. And then we add all this up, and then we can get these two values here. And so from here, basically, I wanted to condense the table into something you could see on the slide. So I took these numbers from each of these groups of cells, or each of these, I guess, yeah, these cells. So EX54, EX squared is 502, and you can see that's that right there. So this is just a reduced version of the table on the previous slide, if you get confused at all. Okay, and so we got that, and then, yeah, a bunch more notation. Again, I'm not going to get into details at this point. Just pay attention as you have been doing. Sort of intermediate calculations here. Click through slowly in case you want to pause and come back to them. Do all this stuff, and again, here we're looking at the scores we calculated at these points in stage 2. Frustrating amount of math, I know. But once we have all that, we will complete the F table. And here it's pretty straightforward as per usual. We just need to plug in some of the squares, degrees of freedom, mean squares, and F obtained. And yeah, and so again, here you can see these are our 3 F scores that we're obtaining, our 3 ANOVAs. So we here have a main effective factor A, main effective factor B, and an interaction. And if we plug all of it in, here's what we see. We see that there is a significant main effective factor A, no significant main effective factor B, and a significant interaction. That's just, yeah, I guess I'm telling you that because this isn't a stats program telling us. But if we just ran Jamovi, for example, and we saw this, that's what we can interpret right off the bat. Here, though, since we are doing this by hand, we need to make decisions for each. So we get a critical value, and then we will obtain that critical value to the obtained value to determine if we should reject or retain the null hypothesis. So for example, the main effective factor A is significant. Here factor A, so our degrees of freedom are 2 and 30. So we'll use those to look up our critical value of F. And our F obtained for A is obviously much greater than 3.32. Therefore, we will reject the null. Factor B is not significant. New degrees of freedom of 1 and 30. We find our critical value. FB is 0. So clearly, yeah, retaining the null. And then the interaction is also significant. We'll use this. We'll have the same critical value as the main effective factor A in this case, and then we'll reject the null, right? Comparing the F obtained to our critical value, right? And there you have that. And so as per usual, we need to look a little bit more closely. If the main effects are significant, we can conduct post hoc tests, basically just like we've done previously. It's like an individual ANOVA at that point for that specific main effect. We just want post hoc tests to further interpret that. Good news in Jamovi is that it can do this automatically for you. And then if the interaction is significant, we will first use simple main effect tests. And so, yeah, so basically here it's like, yeah, we're looking at the interaction by comparing the mean differences or simple main effects of one factor at each level of the second factor. So it's kind of like an ANOVA of ANOVAs almost. So like, yeah, I wish I had my table in front of me. I think I'm about to explain it here in a sec. Here's the decision tree if you'd like it. Yeah, and so yeah, let's get into that more. The simple main effects test. So yeah, choose how to describe the data, choose simple main effect test, compute pairwise comparisons. So yeah, we can analyze rows, analyze comments. This is a noisy thing. So let's for example, let's just dive into a specific one. So let's say here we wanted to do this. We could compare the top 3 cells in the original data via one way between subjects and ANOVA. So in other words, we're comparing. It's like we're doing an ANOVA just with this section of the table, right? So we're looking for differences in group means of factor A when the buffet was absent, right? And then we can do another ANOVA across levels of factor A when the buffet was present. So when I say ANOVA of ANOVAs, it's kind of what I mean is that we're taking a specific piece of the ANOVA and diving in more depth in one of the levels of one of the factors. And the other factor, we're still looking across groups. So for example, if we did this top ANOVA here, this is what we would see, and therefore we don't have a significant F statistic, so we decided to retain the null. In other words, increased exposure to sugars does not interfere with completing the computer task when the buffet is present. I'm sorry, when the buffet is absent. Wow, I'm sorry. I need to stop recording these at night. Um, yeah, because we're looking at it here, right? And so basically we did not find significant differences in low, moderate, and high exposure to sugar groups in their computer task completion time when the buffet was absent. That's what we found here. We'll repeat the same thing for the bottom ones. So now we're looking for group means and computer task completion time across low, moderate, and high exposure to sugars when the buffet was present. We do that, we find a clearly significant F test, and therefore we can say that increased exposure to sugars does interfere with completing the computer task when the buffet of sugary foods is present. All right, so there you go, straightforward. So now if we wanted to go even further, we could compute pairwise comparisons. Yeah, these are similar to everything we've done before. And I don't think I'm going to ask you to do this in the practice exercises. So we can just go ahead and avoid all the nitty-gritty conversation about this. Yeah, okay, yeah, this is just for the reflection on what we just talked about. Effect size, we can do eta squared or omega squared, same as always. Equations, you can do them. And yeah, to summarize, basically this is an example of what it would look like in a paragraph. I apologize. I know I kind of went through that quickly. Part of that too is just my own bias here in that like there's a lot to take in this particular module. So I don't want you to get so lost in all of the nuance that you don't really retain or understand any of this. So focus on the basics of what's happening. The practice exercises should kind of walk you through all the steps just like usual. And then once you've done it, then I would recommend going back and looking further at that nuance if you'd like some additional help understanding it. But yeah, we'll go ahead and stop there, keep it a little shorter. We'll see you next time.